a real course in symmetries. Symmetry. And it's just a name I made up, so it doesn't mean much. Modern geometry. And I use the word modern because I wanted to emphasize this is not just symmetry in Euclidean geometry in the sense of Euclid, which is also very interesting. But in modern times we have symmetry in all sorts of different geometries. And I want to underline the importance of these symmetries. And at first, though, we have the following classical question. This is really Euclid. Classical, let's call it question. It's related to the definition of symmetry, which is somehow very difficult. And I asked this question to my grandson. I'm always telling you I ask him questions. And so I draw a picture. We can do this on Skype or Facebook of a square. I ask him to draw the square. It's always better when you're having a relationship with a young kid to ask him to do everything. So I asked him to draw a square. And he liked very much calling it S, so let's call the square S. And you ask the silly question, what are the symmetries of S? So question I always write, Q, what are the symmetries of S? And you very quickly come to the question is what is a symmetry? So this is question 1, and then question 0 is what is a symmetry? So what is the title of this course? What does that mean? And one of my goals today is to make that precise in the very first lecture, what is a symmetry? But I think in this case here, what Euclid and what my grandson is thinking about is we have the plane here. Of course, the plane is infinite and so on. So this is the Euclidean plane, and to emphasize it's the Euclidean plane, I call this E with the special tech command. I call this E the Euclidean plane because it's much more than a set. It's a set with structure. So this is a Euclidean plane, and it's a set with structure. Maybe I'll even say, i.e., in this case, geometry, with geometry. And someplace in this Euclidean plane, you have this square. It doesn't have to be in the middle. You have S sitting here in this Euclidean plane. And if you try to pin down somebody to say what are the symmetries of S, what they really are saying is what are the symmetries and motions of the Euclidean plane that stabilize S. So you look at the plane, you see the symmetries of the plane, you see what goes on with Euclidean geometry, and you say, which one of those so-called symmetries, reflections, rotations, all of these things you learn in school, what of all these things, what do these things stabilize the plane? Maybe the question -1. So we work backwards with questions. Question -1, what are the symmetries, or what is the symmetry of the plane, of the Euclidean plane, which stabilize the square. So that's the question. And there's some words in that question, so let's try to be so precise. So let's say a symmetry at first. So the trivial version of symmetry now my grandson can't say this, only we can say this, is just a bijective map. Bijective map means it's a map that goes back and forth between, it doesn't change, it's just bijective. So remember, if you recall what that means, it means that if you have, I'm going to call it, so for example here, a symmetry of this should be a bijective map of the Euclidean plane into itself, bijective. That means you can reverse the process. That means that the C inverse exists. And sometimes in tech we just write both ways because we don't care. The command is left, right, arrow. In tech, right? That's the reason it's there. So it means that it's something that identifies this Euclidean plane with itself, and it must be bijective. Bijective, remember, just to remind you, in case means it's one-to-one, so injective. And so one-to-one is sort of a nice way of saying it, and onto, which means surjective. So already we have really some notion of what could be a symmetry, just some bijective map. But I hope you realize that a bijective map is a terrible thing. It can be just unbelievably terrible. A bijective map, can you imagine, you've all had analysis one that I see these guys who were talking at lunch. You know, it's just terrible, bijective map, say from the real numbers to the real numbers. Bijective. So a terrible bijective map. I mean, you have a map from the real numbers to the real numbers, and this thing has a graph. And when you're in school, everybody writes a graph like that, or you say, well, it has a little singularity, it jumps like that, or something like this. But you can just think of what is a bijective map from the real numbers to the real numbers. It's anything. It's essentially anything you can think of, right? So that is somehow a ridiculous definition. It is not a definition. It's just an obvious thing that you need. It needs to be. You identify the plane with itself, so you need that. So you need more. You need more than bijective. So what we learn in mathematics is to think about the Euclidean plane. The Euclidean plane, we need to think about the question, another question, what is an affine space? So the word here is affine. Okay? The word here is affine. Okay? And even better, let's be precise, what is an affine space modeled on a vector space? V. Okay. So I I know some of you, I know these guys here, we just had lunch with these guys, so you learned from K-von analysis 1, and maybe also you learned some linear algebra, matrices, and vector space is okay, right? Things like that are okay, right? Yeah, so you just have to stop me if I'm assuming too much about vector spaces or something. But this is a model on the vector space V. And let's call this affine space, let's make a letter for it, A, that way, model on the vector space V. Yeah. This means that, now I'm going to write some words here that you're going to have to learn when we're talking about this kind of thing, that V, the additive group of V, I'm going to explain this. The additive group of V acts freely and transitively. Look at all these words. Additive group of V, group, additive, acts freely and transitively on A, and that's it. Yes?
Does A have any structure? Is it a set or is it?
I can't hear you as usual.
Does A have any structure? Is it a set? Is
No,
it
I said it's a set.
It's a set.
If your word, I use the word space here, so it's implicit in my discussion that it's a set. Okay? Okay, but there are many words here. I'm writing these words perhaps for me so I remember what to say. Okay? So let's keep in mind, it's an additive group of V which acts freely and transitively on this. So there are many, many words. You see, I tell you, in order to think correctly about the Euclidean geometry, the Euclidean plane, you must think about an affine space, and you must think about many, many different concepts, which I will now talk about. Okay? Okay. First of all, vector space. Some of you are physicists, so this is well known, and to more mathematicians who thought about mathematics a lot, it's very well known. A vector space, V, it is a vector space. So you have two operations. On V, on a vector space. One, addition. So plus, you take a pair of vectors and you can add them. Now I assume everybody here has no problem with school mathematics, that if you take a vector V, you take a vector W, you have to understand every professor in mathematics has taught engineering courses. And so you write arrows at the end of vectors, but there's no such thing as an arrow at the end of a vector. It's this point in the vector space, right? There's no need for an arrow, but if you teach engineers, you need an arrow because it means it goes like that. And so you take the parallelogram here and you fill it in, and you get V plus W. So you can add vectors. Now, a good example. And we will use this example all the time, is V is the n-dimensional, here's this is the two-dimensional vector space. If you have two dimensions here, R2 is the n-dimensional vector space, and an element of the n-dimensional vector space V in standard group basis is written as x1 through xn, and you pay your money and take your choice. Life is capitalistic, whether this is a column vector or a row vector. Right? You never know. It depends on what you're doing, so let's not worry about it too much right here. This is here, and I wrote it as a row vector. So that means in the standard basis. And the standard basis of Rn is E1, that's just this thing. So that's a special vector. And then E2 is the second special vector. And that's like, here's E1, and here's E2. All right, and you have all of these special vectors up to En. And every x in this vector space, every v in this vector space can be written in these coordinates, x1, E1 plus xn, En. Right? Right? Okay. Now make sure, I'm not going to talk about this for an entire course of mathematics. This is school mathematics for me, and it may not be for you, so make sure you have that in your head. These are the coefficients of the standard basis, and this is the vector v written in these standard coordinates. That's the meaning of this expression, v equals x1, E1, xn, En. A lot of physics people here always say, so if you're a physics person, you just write xi, ei, and you forget the summation because there's so many complicated indices. So, of course, this is a sum, but you never write it. Okay, that's the addition. That's the operation of addition. And then there's the operation of what I call scalar multiplication. This was the operation of addition. So V1 plus V2. Well, I didn't write it. X1 to Xn in coordinates plus Y1 to Yn in coordinates. You just add the coordinates. That's completely clear what you have to do. And then scalar multiplication, we write it as V gets multiplied by a number. Right? And you should have a picture in your head that's naive but helps. And again, in two-dimensional space. In two-dimensional space, if you have a vector V, and you might multiply this vector by 27 times V. You can, yes, in Germany, it's called a dilation. Yeah, dilation. Okay? You agree, it's called a dilation. Oh, you don't know this word? Dilate, to dilate? That means, well, I've thought of many dilations, but I won't say them. Okay. That's called a dilation. In German, some of you speak German, it's called Streckung, and it means to somehow stretch it a little bit. So maybe I should always write the German word here so you learn some German. Streckung. Oh, I forgot. Not Streckung. Streckung. That's called a dilation. And in this case, here, lambda is the number 27. For example, here, if we have this vector here, then maybe it goes back to here. Let's say here, then the number, this is lambda v. This might be minus 2v. It can go both ways. Okay. Now, in the background of all of this is the notion of what are the allowed dilations. In other words, what is the number lambda? What kind of a number is this lambda? And we fixed this in our discussion that lambda is a number, it could be a real number, or a complex number, or any number, but it should be in a field. So some field, that's a field of the real numbers, that's a field of the complex numbers, maybe a finite field, and something in cryptography. This is the field of of definition of the vector space. So you can draw the picture if you want. You have a vector v, and maybe here is the vector I times v, where I is a complex number. Don't worry about it. Don't worry about it. You just multiply it and that's it. Okay? So those are the two things that are allowed in a vector space. And you have all sorts of wonderful things. For example, multiply sum. And I mean, there are really a lot of trivial things. If you can sit around thinking about these trivialities, you'll get them all right, and then you'll be bored, and then go to take a glass of cognac and smoke a cigar, and you'll be happy again. So these are the axioms of a vector space. If you're worried about it, check it on the web. Okay, that's a vector space. So what I promised you I would talk about the additive group of a vector space. And I just told you what addition is in a vector space. And now I have to tell you what is a group. So this subject is very wordy at the beginning. I have to tell you what is a group. So a group. So a group G. And now, Maria, this is a set. It's a set. It's a set. Okay, this is dedicated to Maria. It's a set. Equipped with a mapping let's see, let's give me some space here. G cross G to G, which we regard as multiplication or addition or whatever. And we write it, a pair GH in G cross G gets mapped, and I write it multiplicatively. G times H. But that can be anything, any kind of operation, just G times H. You can go home and tell your mother, it's anything. It's multiplication, it's whatever you want. So it's completely arbitrary here. But, of course, which satisfies some rules. And here go the rules. G, H, K equals G, H, K. And of course, you know that rule is called associativity rule, right? So let's write it here, associativity. And that's the first thing we need to know. And another thing we need to know, there exists a special, this is a fantastic set, exists a special element in this group, E, so that E times anything equals, and probably maybe I should write on both sides just for fun, I will, anything times E equals anything for all G. For all G and G, there's an identity. And finally, these are the axioms of a group. Associativity, the existence of an identity, and the following axiom for all G and G. And there exists you can go backwards. A G inverse and G with G times G inverse equals the identity. You may have seen this a little bit in your basic structures in analysis 1, maybe with scalar. The real numbers obviously form a group like that. You've seen lots of examples maybe. We will study many, many examples, but the first thing you should see is the vector space with its additive structure is a group. So this is pretty stupid. You want to check that V U plus V plus W is U plus V plus W. That's the associativity, right? And then U plus 0. So the operation is here plus is equal to 0 plus U. You don't do anything, is equal to U. What do I need else? That's all I got. Oh, I have an inverse. U plus minus U. That's minus 1 is the scalar, is 0. So those are the three axioms of group are fulfilled for the additive structure, additive group of a vector space. Okay. Now this group is what we call commutative. This means that it doesn't matter which order it is. Many of our groups, in fact, I think most of the groups which we will consider are not commutative, so we'll immediately get to many, many non-commutative examples. For now, let's just leave it at that. So, what did I say? Where's this affine space? An affine space is a set A, yeah, modeled on a vector space V, which so that the affine group of a vector space acts, oh, I need to write that, what that means, acts freely and transitively on A. Okay. Excuse me. Okay. We better have some examples of this before we start. Let's take, for example, let's just take a stupid example. V equals the vector space R. Okay, this is everybody's here as analysis 1, even you from me, so it was wonderful, right? It was just, that's Donald Trump speaking. Wonderful. Great. Analysis 1 was great. Particularly when I give the lectures, it's great. Yeah, great. You, of course, it's great. Yes. So that's a vector space, right? That's a vector space. Everybody understands you can add two real numbers and can multiply by scalar. That's a perfectly good vector space. Okay. And now I'm going to let the set A be the set of real numbers. Now this is, Maria was talking about what is a space of a set. I mean, this is also a set. Yeah? And now I'm going to look at an action of this group. It's so trivial you may be confused by me here. Action on A. Well, if I take T in V, by the way, I'm thinking about the word translation. And then the action is I take a point X in this space, and I map it to X plus T. I translate it. I mean, it's not very hard, right? So I hope you understand. I have the real numbers here. By the way, I'm not going to write 0. I'm just thinking of a set. I don't care any of this. This is a set. The trouble with everybody in this room except for me is that when you see the real numbers, you see 0 and 1 and 17 and 84. I'm just talking about the real numbers as a set, right? But I can, the real numbers you can add real numbers. So I have an action of the real, starting with the real number x. I am allowed to translate it. So an affine space is a set equipped with a good notion of translation. Okay? And now I'd like to make that precise. What does it mean? You need to make these things precise, and probably you don't worry too much, but I worry a lot about making things precise. What are the words that are going on here? Additive group of the vector space. So that's like here it is. This is the additive group of the vector space. V acts freely and transitively. So I have to understand the word act. Okay? You have to stop me now. It's going to start getting hard. Because these are starting to be new. These are going to be some new things for you. Right? What does it mean to act? So a G action. G is a group if I write G. So I'll emphasize it one more time, but if this is a group action on a set X. So I'm thinking of the translation group acting on the real numbers. Right? I take Nicholas here and I act on him. You just think of this model and you won't forget it. I'm not going to act on you, don't worry. Okay, but he's much bigger, so you're also probably, you could take me out of it. Okay, I'll act on him. He's over my side. I take him and I move him. Right? I'm going to translate him by something, so I'm acting on upping. Yeah? Yeah, I'm acting on somebody. Yeah? Okay, Kristen. It's okay? I'm not going to act on you yet. Wait. Okay. So a G action on a set X, what is it? What is it? I have to say what an action is a map. And we write it, a pair gets mapped to G of X. Okay? So if G is the translation group, let me write here R plus. That's the additive group of this vector space. And X is the set R equipped with it. Then G cross X to X is what I just did. Is as above. T, X, you give yourself a translation and a point, and you act on it. You give yourself here Uppik. No, Uppik is X. Uppik is the guy I'm acting on, and I'm going to translate him with T. Okay? So, that's the example. And it's just such a map. Now, this map has properties. Properties of this map that are required. Well, the same thing, associativity. G, H, acting on X. If I take Uppik and I translate him, and then by a combination of translation, I translate him by 6 inches to the left, say. I translate him by 6 inches to the left. That would be 6 here. That's the same thing as translating him by 2 inches and then translating him by 3 inches. 4. Did I get it right? 2 times 3 is 6.
Oh, it's not applicable?
Hmm?
Isn't it additive?
again, he's worried because I've written this multiplicatively. I write in all definitions, in all abstract discussion, the group operations, the action operations, everything, I write multiplicatively. It's just an operation.
Yeah, but I mean, it should be 4 plus 2 or 2 plus 4.
Okay, that's 2 plus 4 is 6.
Yeah.
In here is plus.
Yeah, okay.
No, he's right, it's a confusing thing, right? But when we're discussing abstract group theory or group action theory, we write things always multiplicatively.
Why?
Okay? Yeah. Abstract. You don't believe me?
Oh, I just asked why.
Why? Because I have to. What do you want me to settle on? If you write here what we're talking about, you want me to write this, right? All right, that's what you want me to.
Oh, my question
No,
was,
maybe you want me to write this. You don't want me to write that?
no, my question was like, why did you choose multiplicativity over all of the other operations? What makes multiplicativity?
Well, maybe that's not even multiplicative. It's just an operation there. Maybe I shouldn't call it multiplicative. It's just some operation, whatever it is. Okay? But it looks like multiplication. It just confused you, right? I mean, because it looks like multiplication. But of course, if you're writing addition, if you write something like this, then you're immediately going to say that's the same as h plus d because you believe addition is commutative. So don't write addition unless you're sure it's commutative. Okay? So that, okay. Okay, this is a property. That's more or less the associative property. And the second property is the identity doesn't do anything. Okay, you believe it. The identity should not do anything if it's in the group, right? Okay? Now, this was a little lecture, and I'm going to continue lecturing, but I want to say a little bit of history. The definition of the group, notion of a group, was made in the middle to late 19th century. Even at the level of a great mathematician like Hilbert, Hilbert was interested in when you would talk about a function and then you change with a group operation, which might be a linear transformation of x1. I'll write it here. Hilbert was very interested in what will happen when you put in an operation on the variables in a function. I'll say it again. Hilbert was interested in functions and variables and interested in what happens when you put in an operation. Hilbert could not write in his work the action, what is a group action. He called this a substitution. Okay. This is a very interesting thing. This definition of group was, of course, implicit Galois, but this is explicitly written in work of Jordan. And what I'm explaining to you here about actions of groups and groups is, in some sense, very modern mathematics of the 20th century. It's very interesting. And the point is, if you look, and you do look all the time in the web, as I do too, for the definition of symmetry, look in the web for the definition of symmetry. There will be nothing but blah, 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 blah. Nothing is precise. And the reason is, you need fundamental notions. And these fundamental notions, group action, yes, and what are they really dealing with in this stuff, happened very late in mathematics. So I ask you, please, don't just go blah blah, there's a symmetric guy, here's got a left hand, a right hand, they look right, and he's cool. Yeah. No, there's an appendix on this side, so it's not symmetric, or it's 2 legs and 1 and so on. I mean, it's all blah blah. Yeah? So in every discussion, I started with a square. After all of this very precise mathematics, what is a group? What is a group action? What is an affine space? Yes? You need to have these things in your mind. What is a group? What is a group action? What is an affine space? I'm not even finished with affine space.
Oh, yeah, okay.
Yeah, he caught me as usual. Okay, where the devil is, oh, I'm sorry, so we have to do it, very good. Okay, you take the additive group of a vector space, and it should act on the affine space. And you should think acts by translations. And it should act in a good way, with two words, freely. It's democratic. Freely, the land of the free. My homeland, with President Donald Trump. The land of the free. There's no such thing as freedom, particularly in that land. So, must add freely and transitively on this. So I need to define these two words. Well, let's see here. I really like my pictures here. So I'm going to leave this picture here. I'm going to do some erasing. So finally, two more words, and then we have enough words for a while. The two words are right there. That's what Mr. Weiss was reminding me of. Freely and transitive, what I need to, know. So free, the land of the free. So a free action. Means if G is in G and X in X with G of X equals X, okay, if you have an element of the group and it's acting, we have an action. And you see what happens, you take an element and you apply G to it and it fixes it. So there's a notion here, X is a fixed point. Okay, we say X is a fixed, Gx is fixed by G. Well, X is fixed by G. Then the condition is that G is the identity. So only the identity fixes something. Yeah, that's interesting. Only the identity fixes something. Right? So now you should always carry around an example. Example. So V plus, the same thing as above, equals R plus, acting on the set R by T x goes to X plus T. You translate X by an element of R. I hope you see the only possibility for a fixed point, so that means X plus T equals X, is T equals 0. right? That's the only possibility, right? So that's what the statement means. If g of x is in g, and x is in x, with g of x equal x, then the only possibility for that is the identity. Okay? That means the action is free, is a free action. I hope you're going to see, we're going to work on the square in a minute, maybe. Here's a diagonal, and here is a reflection across this diagonal, right? And this reflection takes x to, let's call this x1 to the reflected x1. But this is x2 and this is x3, and you see the reflection of x2 is equal to x2, and the reflection of x3 is equal to x3. So these are already points that are fixed, even though some points are not fixed. Okay? Some points are fixed, some points are not fixed. Okay? The action is free, means no element fixes any point. Okay. That's a free action, so let's look again. The additive group of V acts, and we should think by translations on A, freely and transitively. Well, transitively means something very simple. Transitively means you have a G action, and you have a set which is very, and we take a point at X. And then we have an interesting set, which is everything you can get by acting on X. Okay? Now you can see this is the ideas here. All the points, I'll write it in slang, points in X that you can get. You should never write this for yourself, but for feeling, you can get from X by acting by the G action. For example, if X is equal to X1 and G is the group generated by the identity and this reflection, so just the group of order 2, so the order of this, we write order of the group is 2 in this case. The identity, just one map, the reflection, yes? If X is X1, then G of X1, so I'll write X1 here again. Well, it's X1, and it's the reflection part, X1, which maybe I should write X1, X2, X3, I'll write this as X4. So this is the element X1 and X4. Everything you can get by acting by the group, in this case it's just a reflection, it's 2 elements, it's a group action on the corners of the square. Everything you can get are these 2 points. Okay? Okay. Now, that is, oh, by the way, you need a word for this. This is called the G orbit of X. Okay. The G orbit is a little hot in here, right? Would you mind if you open it a little bit? Just a crack? A little bother you? Okay. I can't open it anymore. Maybe. And, okay. Yeah. Can you open that just a shade? Yeah, let's do that. Huh, they've locked us in here and now. Okay, that's great. Thanks. This is the g-orbit of X. And transitive means the g-orbit of any point equals everything. It doesn't matter what point you take, just take one, and the g-orbit is everything. That's the meaning of the transitive. And you look again, if you have the action of the additive group of the vector space on R, so that what I was doing before, on R as a set. Again, it's X is mapped to X plus T. You get everything. It's completely obvious you get everything. And this action is free. It's a free transitive action of the additive group of a vector space on the set. Okay? Now in mathematics, I mean, some of you are physicists, some of you are computer science, some people are beginning mathematicians, some of you people are advanced mathematicians. Yeah. But I will tell you, it is very important to really cleanly have a definition of something in your mind. If you don't have it in your mind as a good definition, you can't do anything. Yeah? So you must have it in your mind. So when you're in the shower in the morning, you're enjoying this beautiful shower. I have a little bit of back pain because I'm always in front of a computer but I'm enjoying it, and I put my back here. It's very nice with the hot water and so on. I don't say this, but you could say an affine space is a set dedicated to Maria. Well, it's okay. She's right. I mean, some things are not sets. So an affine space is a set equipped with the action of the additive group of a vector space, which is free and transitive. And now watch. Now we're going to start with Crystal here. And I'm going to translate her all around this front row. All right? Let's say that it's a finite additive group. It could be, right? It could be a group of, I told you, it could be a field, a finite field. So maybe, right? Let me see how many there are. 1, 2, 3, 4. Oh dear, it's an even number. So let's assume there's a five. Only you don't count. So let's assume we have 5. We're able to translate her by 5 elements of this field. Right? Here. Oh, 5 elements. It's okay. It's cool.
You can.
Yeah, you can. That's cool. I identify her by the translation that I used from Crystal to get you. I identify him, not because he comes from Ho Chi Minh City. You do come from Ho Chi Minh City, maybe. You too. See, that's the problem. They both come from Ho Chi Minh City, and so we can't identify them by that quality. But we can identify them by the unique translation that I used to get you from Crystal. And I can, to get you, Mr. Pham, right? To get Mr. Pham, I have another translation. And to get Nicholas and Abik, I also have other translations, right? That means I'm really identifying the people by their translations. Yes? It means that if I fix the base point, Crystal, I identify the rest of it by the translation. If I fix Nicholas as the base point, I use the word base point. It doesn't mean anything negative about you. But if I fix you as the base point, I identify everybody else here by the translation it takes to go from you to the other person. Right? That means that if A is an affine space, now let's write it here where we have some. Here's the definition, so I can write it again here. This is good. So what I just said, I'm going to say it again about crystal. Okay? So if A is an affine space modeled on V, and now we're going to have some fun. The base point I'm going to call crystal, the fundamental point, right? Obviously fundamental. And P0, maybe I'll call it A0, no, I'll call it C for crystal, is a base point. I'll call it base point in the discussion. Then, here we go. A is the same thing as the orbit of the base point. Right? A is the same thing as the orbit of the base point. I just proved it for you. I hope you understand. There's Maria again. She's going to ask a good question.
So if the group action is not free, then it cannot be transitive.
That's right. That's the reason we need free and transitive both. Because if there were two translations which took crystal to U, I wouldn't know which translation to choose. Right?
But doesn't transitive imply free?
No.
Okay.
No.
Why not?
We will have many. So Maria asked, she's worried, and she's asking good questions as always. She says she worries that maybe transitive implies already that it's free. Maybe it's a reasonable question, I don't know. But let's take the group. We don't know yet what the group of symmetries of the square is. But let's think of the group acting on the four corners of the square. It is completely obviously transitive because you have the rotations that take around it. But you also have the reflections. So it is not free. Right? Right? It's not free. So you have a question too.
Yeah. Are we assuming that the action of G on the set X is commutative because
No.
we are saying that?
No,
So it's only from the left.
that's only in this example.
Okay.
So thank you. I used it. The translation, no, it's a very good question. The translation group itself
Mm-hmm.
is commutative.
Okay.
But the action of the translation group, okay, it's just some group action. Okay?
So it doesn't matter is GX or XG, right?
Hmm.
Or
Say it again, please.
GX is the same as XG or not? Here in the definition of transitive.
Well, I'm lost. So where are you talking?
Transitive equals G.
The G orbit of X from left is the same as from right, or
I should write this as this. And now there's no preference. Just the translation applied to X. Right? I have a certain translation applied to crystal and I get this. Yeah? Whatever it is. In the example, I was writing the translation just addition. Right?
yeah.
But, okay. Okay? Very good, thank you. So that's the situation. Let me now. I have a recommendation for this first lecture that I lecture until about a little bit after 6, so you have most time to go to dinner. Normally we would have a pause, a break, but I think it's good to get to dinner a little bit early if you want. Okay, so I will have no break today, okay? Okay? Ready? You Euclidean plane is E is the affine space I will emphasize its dimension A2 modeled on the vector space R2. So I lecture almost for an hour to give you a silly thing like that. But it's not so silly, maybe. Okay? The first point to keep in your mind, in my opinion, is in the Euclidean plane, there is no standard base point. You draw that picture here of the square in the Euclidean plane, it's somewhere. There is no 0 point in the square. In Euclidean geometry you had in school, you have a triangle here in the plane, and you have another triangle here in the plane, and you make noise about the triangles being congruent or something like this, right? But you never use any particular base point, do you? In fact, don't you always use translations? Yes? Isn't it true that in the Euclidean plane, you use the translation maybe all over the place, you don't care? Okay? So the Euclidean plane is the affine two-dimensional space modeled on this vector space. That means, in particular, the Euclidean plane is equipped with a two-dimensional group of translations. I mean, the one that define the affine structure by R2 plus. Nobody can tell me in physics, so there's some physicists here, I know many of you. I look around, know some physicists here. Nobody can tell me in physics that there's a canonical point in the world. You know, this is probably, unfortunately, this is probably some fundamentalist religion. There's a God. You see, these people say there is a God, and that's therefore, the word canonical comes from religion, actually, canon. Or for me, it comes from music. But people will talk about God being the fundamental point in our universe, or something like this. There is no canonical point in physics. This is a fundamental fact, right? There's no canonical point in physics. There is no 0 in physics, right? However, in many situations, the physical situation of relevance is equipped with a group of translations, right? So the physical group of relevance, for example, for three-dimensional elementary physics, might be three-dimensional affine space, a group equipped with the group of translations of R3. You can translate the variables any way you want, but there is no 0. There is no base point. I mean, Nicholas might think, no, he's a modest guy, but you know, I'm a base point. So don't think you're not. Nobody is a base point. You got it? Okay. So that's okay. So again, symmetries. Of the square in the Euclidean space E is the symmetry. Oh, let's be precise. The symmetry group of S in E is The stabilizer, I'm writing big words here, the stabilizer of S in the transformation, so I'm going to write it E2 of R, which is the group of symmetries of Euclidean geometry. Okay, yes.
So in the case of the Euclidean plane, the group of symmetry is R2 plus, right? So do you call the vector space after which you model the affine space the group of symmetry of that space?
The group of symmetries of the, which is, I'm calling E2R, 2 because it's the two-dimensional Euclidean space, is the group of symmetries, whatever that means, of this thing. And the first remark I think you are making is, I will note what you're saying, I think, is R2 plus is contained in this group. Obviously, R2 plus, that is, those are going to be symmetries. Yes? R2 translations are automatically symmetries. That's what you're saying, I think, Marita, right? But don't believe that this is going to be that. Okay? So let's now return to the square. To S. And we hope to describe what I will call, I'm going to write down now a terrible notation. You should never write this notation because it's too complicated. Okay? Describe E2R, those are the symmetries of the plane, S, which is the symmetries of the plane, Whenever I write something S like this, which stabilize S. G of S equals S. Do you have it? Isn't that a terrible note? It's way too much. Right? So you have the big group. So here you have the big group acting on the big plane. And you have the little square. And if you're stupid, you think there's a translation that stabilizes the square, but you're not stupid. You notice that no translation stabilizes the square. It's obvious, right? No translation is going to stabilize the square. So we're interested in what are the other ones which stabilize the square. So there could be translations, because Maria pointed out that the translations are contained in this big group. But there may be more, I hope. Well, we just saw some. Yes, Nicholas.
How does the Euclidean plane act? How does the Euclidean plane act on something?
Oh, I hope I wrote something wrong. Where did I write?
No, how does it act on? I mean, if it's a group, how does it act on something?
No, the Euclidean plane doesn't act on anything. This,
Or, I mean, something Euclidean plane, how does it?
well, yeah, well, this is the group of symmetries of the stabilizer in this. Okay, which is the group of symmetries of the Euclidean plane?
Because I don't understand. So you say G is an element of the Euclidean plane?
Oh, I maybe.
Or is this the
Group of symmetries.
Ah, I see. Okay.
And by the way, yes, I see Maria.
Is the dimension of the Euclidean plane well defined?
The dimension of the Euclidean plane.
Because can't you just, act on it with R3 or something of dimension 3 or something of dimension 4? Why can you?
Well, she's asking the question, what the devil is this?
Yes, basically.
Yes? And I purposely have not yet defined it, or not understood it anyway. Again, it is very interesting. We're dealing, believe it or not, with non-trivial notions, right? So I start this question by asking, what are the symmetries of the square? I answer this question by saying, what is the plane? I told you what the plane is, it's affine space. And then I answer the question, what are the symmetries of the square? By saying it's just the stabilizer in the group of motions of the Euclidean space. But I hope you understand I've got a circle going here, right? I'm defining symmetries in terms of symmetries, right? There's something really wrong with this. Okay? So I've got to get my foot in someplace to get a hold of this. Do you understand what I'm saying? That's what Maria is worried about. What the devil is this group of symmetries of the Euclidean plane, right? So the whole lecture, I go blah, 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 and then we have to answer Maria's question, what are you talking about? We're talking about, the rest of it is just some calculation you can do in the shower. Or you don't even have to have a shower, it's so easy. So the question is, what are the symmetries of the Euclidean plane? Translations for sure. Okay? Yeah? But others also. So I think we have time to answer that question.
Question?
Yeah.
Is there a reasonable notion of a morphism between two affine spaces?
Of course I have trouble, yeah. Okay.
Is there a reasonable notion of a morphism between two affine spaces?
Well, sure, sure. Equivariance, so I'll be talking about equivariance with respect to the group translation. That's it.
Okay. And is there just one affine space that's modeled?
Yeah, so that's a very good point. He asked a couple questions. The second question I'll announce to the class. He said, is there just one affine space modeled on a fixed vector space? In other words, Crystal gives me V, the vector space, the additive group, and so on. And the answer is yes, there's only one, because you can write down the isomorphism immediately.
Right. So you can just think of it as you start with the vector space, forget the extra structure.
The point is, what he just said is correct. If you read in many physics books, for example, that an affine space is a vector space where you forget the origin. Yeah, I don't like that definition. But my definition, if you understand those words correctly, is the same. And my definition is the standard definition, so, okay. Okay. So now, we were just talking to Abik, and so we're going to do that. We're going to fix the base point. Okay. So what I'm going to do is, I'm not stupid, completely stupid, I'm a little bit stupid, not completely stupid. We take the square, I'm going to fix the middle point of the square as the base point. Okay? I think it's a very smart choice of a base point. Right? Okay? So, we now apply the identification with R2. Don't forget, this square is sitting someplace in the plane. I don't know where the devil it is. It has a center which is defined, right? And now I'm going to choose the center as the origin. See, Oppick said another definition he hears all the time is it's a vector space where you forget the notion of zero. I'm going to say, in order to get the notion of zero, I have to choose a point in it. It's the other way around. And I think it's psychologically a fundamental point. You really are choosing some point. If you read, for example, the beautiful book of Arnold in mathematical physics, he emphasizes this point in relativity theory very, very strongly. that there is no such point as a 0 point. You have to choose a base point. You know where you are. Maybe the base point. That's Crystal. That's where she is. Maybe that's the base point. This guy is a different base point. Okay. So we choose this base point, and we have identification with R. So now we R2, and now in this identification with R2, that is 0. Okay. Okay. And now we're going to try to answer very quickly because we don't want to keep you from dinner. Maria's question. We forget all the translations because they're no longer relevant. So we ask the question, what are the elements of this group of motions which fix 0? Right? Because if I have something that doesn't fix 0, it goes over some other place, I can translate it back. So I really only need to know the ones that fix 0, right? Okay. And then you think a little bit slowly, what does geometry mean in this case? Well, it means points. That's not such a problem. Lines. I'm going to make a list here. And it means that the elements of this thing should preserve lines. And this is Euclidean geometry, so that means lines are lines are lines are lines are lines. I mean, it's nothing fancy. It's not like some complicated geometry. So a line is a line. So nothing fancy. So we have a line, and we're interested in the transformations in Euclidean geometry of the Euclidean plane. We have a line through here, and a line through here, pink line, and an economic eco line, Greta Thunberg line, green. Yeah? And you want the condition that every line, it doesn't matter whether it's pink or green, so it gets mapped to a line. So it says that the G of a line through the origin is a line. Now, you should go home at night and call your high school teacher, who taught you geometry in a good way, I'm sure, and ask the question, let's call it a project. Describe the transformations, the elements, the mappings, a set of mappings G of the Euclidean plane into itself, say bijective to make it nice, so that G of a line is always a line, is a line for all lines. You get that question? You get the question? Isn't that a reasonable question? You have the plane. You have a base point. Crystal. That's 0 now because we're taking crystal as the base point. That's a 0 point. Everything goes out from crystal. We consider all the lines through crystal. All right? Sorry, but I mean, yeah, all the lines. Okay, those are all the one-dimensional subspaces of R2, yeah, through 0, right? And the condition on, I have a transformation, G, acting. What is the condition? That it takes a line to a line, no matter what the line is. That's an interesting, and in my opinion, very hard problem. You understand the question? I think I've formulated it okay. I never know. Okay? Yeah? So, you want to maybe guess the answer. It's almost a linguistic guess. G should act as a linear transformation. Now, you've had some experience with a little bit of linear algebra, right? Maybe. And you know that a linear transformation takes a line to a line. In fact, that's the reason it's called a linear transformation, is because it takes a line to a line. It preserves the linear structure of the vector space. It takes lines to lines. But be careful. So for those who are a little bit interested in mathematics, I claim that's a hard problem. To figure out what are the transformations of Euclidean space or of R2. I mean, it doesn't matter because we have a base point, which take lines to lines. If you could come up with some elementary proof that that should be a linear transformation, I would be very happy to see it. I only know how to prove that. I haven't thought about it too much, really, but I only know how to prove this for something like a continuous transformation, or a transformation that has a little bit of what we call regularity. It's not just some crazy transformation. You understand what I'm saying? Just because it takes lines to lines doesn't necessarily mean it is linear. Right? So you have a bijective map of the plane. It fixes 0. Why does it take lines to lines? So we will assume that our transformations of Euclidean space are sufficiently regular so that such transformations are linear, such mappings are linear. But I hope you understand, I started at the beginning of this lecture, I'm going to stop now, soon, trying to define symmetry. Let's think about exactly what I tried to do. Yeah, I said, what are the symmetries of the square? I said, you're looking at the square in the plane. So I'm asking you really, what are the symmetries of the plane which stabilize the square? You said, what is the plane? I mean, you ask these questions. You should speak like some guy from New York, not Donald Trump, but some good guy from New York. Hey, what's the plane, man? Tell me what is the plane? That's the way these people talk. They would say talk like that. Hey, what's the plane? I don't know what a plane is. I don't know in Hanoi. No, you're not from Hanoi, but no, of course you didn't say. In Hanoi, they probably say, what's a plane? I don't know. How do you say, what is a plane in Vietnamese? Okay, we should.
I mean, there's many words for plane Vietnamese, like you were saying about plane geometry or plane flying on the
Ah, he's very precise, plane geometry.
Map fun.
Not fun? Your name is Fun.
Fun. This that
Fun. Oh, close. You know these Asian languages, particularly Vietnamese, Chinese, and so on. As a Chinese, the melody is so determines so much the meaning, right? So you need to know the melody.
yeah.
And of course, it's very hard for us to learn the melody of your language. So speak English. Hey, what's a plane, man? A plane is affine 2 space. It's the two-dimensional affine space model of the vector space R2. Right? You can go into the halls of mathematics and scream at the other professors, I know what a plane is, man. And check if they know what a plane is. Maybe they won't. So, okay, it's affine 2 space. We pick a base point. We pick crystal. We put that base point, we pick one that's good for our analysis. We pick it in the center of the square. Then we ask, what are the remaining, this is Maria's question, are the remaining transformations of symmetries of Euclidean space which stabilize the square? And that's going to be the symmetries. Okay? So we replace the question now for what are the symmetries of Euclidean space? Okay? So in the next lecture I'm going to answer that. And once I know what are the symmetries of Euclidean space, I know it's the translations plus something else, plus linear, somehow or another. I'm going to look and see what are the symmetries of the square. I hope you see how hard it is to make precise what the word symmetry really means. And if you look, it'll be very interesting because you know the web very well, all of you. Look at the various definitions of symmetry in the web. And try to avoid making it, see if you can make it precise without using the notion of a group action. I think it's very hard. It's fundamental. Group action, symmetries of the big space, stabilizer in the small space. Okay, let's meet tomorrow at 4 o'clock. Thank you.